Hey, hello everybody. Other pre-calculus C students, we're going to learn about polynomials today. People here currently in the room, we're about to learn about polynomials. Are you ready? This is the new unit. Okay, first thing is first, let's review a thing that you learned last year in pre-calc A, which is polynomial long division. So I shall give you a polynomial long division problem right now, and you will do it. Does everybody remember how to do this?
Yep.
So it's just like regular long division, kinda. Alright, so it's like, how many times is 2x going to 6x cubed? Answer 3x squared times. So you like put that up there and then you just multiply back through. So it's 6x cubed minus 3x squared. And then you subtract. You have to be careful because that's like negative 13 minus negative 3. So that's like negative 13 plus 3. Everybody agree? You like bring down the next term. How many times is 2x minus 1 going to 10x squared? Minus 10x squared. Negative 13 minus negative 3 is negative 10. How many times is 2x minus 1 going to negative 10x squared? Well, negative 5x times. And then that gives me negative 10. And then you multiply back through. Okay, so this is pretty much like coming back. Subtract. Then you get negative 19 minus 5, so negative 24x. Bring down to 12. And finally, that goes in negative 2 times, and you get
negative 12.
Negative 12, I mean. And so you get negative 24x plus 12, and then that's just like 0. Woo! How are we doing? Okay, so this time it went in evenly, and therefore we say that the answer to this problem is just 3x squared minus 5x minus 12. Good? Okay, here's a little preview. A little preview is that you could multiply both sides of this equation by 2x minus 1, and then you get a statement about polynomials. That the numerator is just 3x squared minus 5x minus 12 times 2x minus 1. Okay, division is not real, only multiplication is real. Every division statement wants to be like rewritten as a multiplication statement for like deep understanding. How are we doing?
All right.
Say good.
Good.
Good, let's do another one, another one. So 6x. Go. people at home, you should be doing this also. And then something weird happens with this one. What happens? Yeah. It does not go in evenly, yeah?
Yeah.
Yeah. So we have some kind of remainder, and okay, I don't think we okay, so what does this, first of all, did everyone get the same thing as me?
Yeah.
As I did? Okay, good. So what does this kind of mean? Well, this means that I tried to divide this cubic by x minus 2, and I got this quadratic, but there was like some left over. And the leftover, 46, is like how much didn't go into x minus 2. So you end up with something like that. Yeah? Did you guys get comfortable writing it this way in pre-calc A? Okay, good. All right, so good. What did we do? We divided a cubic by a linear and we got a quadratic. All right, well, gonna actually just very professional video. Let's move over here. All right, so a better thing to do right now that kind of better illustrates what's going on is to, once again, rewrite this as a multiplication problem. So really we're studying polynomials here, and the better way to understand this is to say that the polynomial 6x cubed minus 3x squared plus 4x plus 2 itself can be expressed as this 6x squared plus 9x plus 22 times, does everyone see what I'm doing? I'm multiplying through by x, I'm multiplying both sides of this equation by x minus 2. And this then just gives me x minus 2 plus 46. Okay, and we have actually names for all of these things. This thing on the left-hand side, this cubic, is the thing that I started with, right? That the thing that got divided. Does everyone remember what this is called? Old-fashioned term? This is the dividend. If you had a old-fashioned or maybe just old or both elementary school teacher, maybe they taught you all these words and expected you to know them. The dividend is like Latin for like, you know, the thing which is divided or something like that, right? So that's the thing you start with. And then this thing also has a name.
Divisor.
Careful, x minus 2 is the divisor. The divisor is like the thing that does the dividing. But then this quadratic is what happens when you do the division. That's called the quotient. Yeah. So this is like the quotient. And then finally this is the remainder. Okay, so what's really going on here is we are learning a fact about polynomials. And the fact that we are learning about this dividend polynomial here on the left is that it can be expressed by dividing through by x minus 2. What we really learn is that it can be expressed as this quotient polynomial times x minus 2 plus some kind of remainder. And these are all going to be polynomials. So sort of more generally, given some polynomial p, one may divide that polynomial by some divisor polynomial and get some kind of quotient. So it's like this. And the quotient, and also some kind of remainder. Okay, so this is the sort of abstract view of what's going on here. A polynomial can be divided by the divisor polynomial and thus expressed as the product of the quotient, the divisor, and then a kind of remainder left over. All right, and there's a couple of like observations to be made about this. And would anyone like to say anything generally about the relationship between the dividend, quotient, divisor, and remainder polynomials? But there's some things, yeah.
No, maybe this wouldn't work. It looks kind of like
Just like the setup of that formula thing, it looks kind of like the formula for a linear equation for a line.
Oh, okay, I sort of see what you're talking about. No, I don't think that's exactly directly relevant. Something about the, like, okay, this is a cubic over here, and what do you notice on the right-hand side? Okay, of course it's also a cubic, but more generally, or maybe just, yeah, Eric.
It's whatever the maximum degree of the divisor's degrees less, I guess.
Okay, so he's bringing up the degree of a polynomial. What is the degree of a polynomial? It's just the degree of the highest term in that polynomial. So that's why we call this a third degree polynomial, this is a second degree polynomial, this is a first degree polynomial. This is also a polynomial, it's a 0 degree polynomial. Okay, so one observation, last chance, otherwise I'll just say it. Based on what happens when you multiply, what happens to two polynomials when you multiply them together? What can you say about the degree?
It increases.
Well, even more specifically.
It's the two, like,
Yeah, it's the sum of the degrees. Yeah, so here, because of that fact, the degree of the dividend polynomial is going to be equal to the sum of the degree of the quotient and the degree of the divisor. Because when you multiply two polynomials based on the way exponents work, the resulting polynomial has a degree which is the sum of the degrees of the two polynomials you're multiplying. Who's with me? Okay, and then there's like another observation. This one might be almost a little bit silly. What can be said about the degree of the remainder? In this case, it's 0, but I don't think it has to be 0. Because what if you're dividing through by like a quadratic or something like that? Then,
One less.
yeah, he's saying 1 less. I think you're close. I don't think it even has to be 1 less, because you could get lucky, it could be even more. Yeah, but it has to be less, right? The degree of the remainder has to be less than the degree of the divisor. And this is just kind of like maybe so silly it's not worth mentioning, I don't know. But this is just true because if it weren't, then you would just keep dividing. Built into the polynomial long division algorithms, you keep dividing until you can't stop dividing anymore. And you can't stop dividing anymore when the degree of the remainder is less than the degree, strictly less than the degree of the divisor. Okay, how are we doing? All right, one final thing before we sort of leave this board. All of this is supposed to build upon like previous knowledge that you had about just like numbers, man. So like, just take 1 minute and do this with numbers. Take 7, 6, 31 divided by 12, for example. Okay, this is just straight up like regular long division. Let's just do it. That's kind of like, you know, fun. 7, 6, 31 divided by 12. And, you know, they teach this in 3rd grade or something like that. How many times does 12 go into 76? Exactly like what we did over there? 6 times, yeah, that's so true. And then you get like 72, and then you subtract, and you get 4, and then you bring down the 3. How many times does 12 go into 43? 3 times, and then you get like 36, and then 71. How many times does 12 go into 71?
5.
Yeah, only 5, like almost 6, but not quite, 5. And so then you get 60, and you subtract and you get 11. And it's possible if you were in a certain grade, I don't know when, you would actually just give your final answer as 635, like R11. You know, at some point they tell you to do that, right? Okay, but really, what does it mean to have this remainder 11? It means that when you divided this number by this number, it went in 635 times, and not quite 636 times, right? So 635 and 11/12. Okay, so this is like normal long division, but since division is not real, one may, once again, rewrite this statement using just whole numbers only. Really what's going on here is that 7631 can be expressed as 635 times 12 plus 11. And once again, we have here, this is the dividend, this is the quotient, this is the divisor, and this is the remainder. And so there's a sort of a deep fact. If you take discrete math here at Blair, or you take some kind of number theory type class in the future, you will learn this fact about numbers, and that is that you can represent any number as a certain number of 12s plus some kind of remainder, and that remainder is guaranteed to be less than 12, because if it wasn't, you would keep going. Okay, it's called the Euclidean division algorithm. All right, good. That was all like warm-up or whatever. How's everybody doing? Polynomial long division back into your brains. This treatment of polynomials is a little bit of vocab. That's about all we've accomplished so far. All right, what I would like to draw your attention to now is a very specific kind of situation that comes up very, very often. And the very specific situation that comes up, I'm going to write this, special case. The special case is when the divisor is of the form x minus a. Okay, so for the rest of this board, and for the rest of today, let's only consider the case when the divisor is of the form x minus a. Cool? Okay, so we're going to learn something about this special case right now, but first we're going to do like a kind of a problem, just to get it up on the board. So I'm going to give you a problem to do right now. This cubic divided by x minus 4. So this falls into our special case. Okay, go. Okay, did you get what I got?
Yes.
Woo! Okay, so relatively simple. You just have a cubic. You're dividing by this linear polynomial. It does not go evenly. And so our conclusion is that, do I even want to write our conclusion? Sure. Our conclusion is that, okay, this is just what we get. All right, how are we feeling about this? Say good. Good. Okay, well, I'm feeling not, what's up?
Wait, 4 plus negative 6 is negative 2.
Did I do something wrong?
No, you didn't.
Negative 6 minus 4 is negative 10. I think I did that right.
Yeah.
Yeah.
No, but
Because you're subtracting. Yeah, it was.
Wait, did I do something wrong?
No,
No, I
you're
didn't. I think I'm good. Okay. Okay, so here's the thing about. What's wrong? Everything's fine?
Everything is fine. There are no problems.
So the
You're
second
good.
line is like you flip the sign. So the second line.
Negative 13 minus negative 12 is negative.
No, but then you do negative
Negative 6 minus negative 4. Negative 1.
negative 1.
Okay, a lot of controversy going on
Minus
here.
negative
It's,
x.
yeah, minus negative 4 is plus 4.
Negative 6 minus
You know what, never mind.
positive 4 is negative.
Are we good now? Okay, good. All right, good. A lot of negative numbers. Our brains were not meant for this. All right, wait, hold on. Class, coming back together. Here's the thing about this algorithm. It's very time-consuming. There's a lot of writing. Let's look critically. People at home, let's look critically at what we have here. What I have here is like a lot more work than is really needed because, first of all, there is a very tight structure to things. I always gotta put my cubic terms here in a little nice little column. I always have to put my quadratic terms here in a little column, linear terms in a certain column, constant terms in a certain column. And one of the things you learned last year, which is kind of common sense, is that you have to leave space for it, right? Even if the quadratic term were 0, who's with me? You have to like leave the space for it, otherwise like you might like mess up and stuff. So, okay. In other words, I can infer the degrees of all of these polynomials by simply counting back like from the right. Do you know what I'm saying? These all have to be the same degree. This is going to be a 0 degree constant term. The next one to the left will be guaranteed to be a linear term. The next one to the left will be a quadratic, the next one cubic. So if you erased all the variables, do you agree that the semantic content could still be recovered? Right? We would still know exactly what's going on, even if all the variables disappeared. Say yes.
Yes.
That's interesting. Another thing that could be noticed is kind of a waste of time is, do you see how I'm writing this in a kind of lame sort of fashion, like over again, like 6x squared times x minus 4 is 6x cubed. This is sort of providing psychological benefit only, right? Because these two numbers in fact have to be the same. If they weren't, like I did something wrong. So I'm kind of like wasting my time like writing this over here. Okay, so I shall now introduce to you a new and improved, more efficient version of polynomial long division. It is called ghost polynomial long division. Yeah. Ghost polynomial long division is just like regular long division, but faster, or is it? Once again, it applies only in the case when I'm dividing by something of the form x minus a. Okay, so watch what happens in ghost polynomial long division. It's the exact same thing, but now I just write less, because I'm gonna, this is like 6, right? But I'm just gonna agree to not write x cubed, because I don't need to. And then I'm gonna write minus 21, and I don't really see, I'm leaving a little blank space, like a ghost, because like they all disappeared, right? All right, good. Minus 13, and then like minus 6, okay. And then, what am I dividing through by? I'm dividing through by x minus a. But by x minus 4. But we agreed that everything I'm about to say only applies to when I'm dividing by x minus a. So I don't even need to tell you that. I could just write like minus 4 over here. Okay. So do you believe that I can still do this problem with if it was given to me in this form? Say yes.
Yeah.
Yeah, of course I can. Okay, let's do it right now really fast. Watch. What am I going to do first? Well, the first thing I'm going to do is I'm going to see how many times x minus 4 goes into 6x cubed. And notice that I don't even need to know whether that's 6x cubed or 6x to the 4th or 6x to the 5th. It doesn't really matter. Because how many times is x minus 4 going to go into 6x to the whatever? 6 times. So automatically, I get a 6 over here, right? X minus 4 just does go into 6x cubed 6x squared times. But basically, the moral of the story is the first coefficient in the dividend automatically becomes the first coefficient of the quotient. As long as we're dividing through by something of the form x minus a. Can I get a thumbs up? Okay, good. Alright, then what's the next thing I'm supposed to do over here? The next thing I'm supposed to do is I'm supposed to multiply that 6 by x minus 4, right?
Yeah.
Okay. But we've already agreed that it's kind of like annoying. I don't need to multiply by x minus 4 because of course that number is going to be the same, right? So instead I'll do the minimalist approach. I'll just multiply 6 by negative 4, giving me negative 24. Cool? Say cool.
Cool.
Okay, and then subtract. It's exactly what's going on over there. So follow, like compare them side by side. All right, then I subtract negative 21 minus negative 24 is 3. And then I just don't even bother writing the variables because they're like irrelevant to the logical structure of what's going on. Then the next thing I'm supposed to do is to bring down this like 13. So I do that. All right, and then what's supposed to happen next? Yes, then I'm supposed to ask myself, how many times does x minus 4 go into like 3x whatever, right? But the answer is going to be? The answer is going to be 3. In other words, he's saying, hey, whatever I get when I do this subtraction automatically becomes the next coefficient in my quotient. Follow? Okay, so I'm just going to put a blank ghost there, and then I'm going to put plus. Okay, and then what am I supposed to do next? Next I'm supposed to multiply this 3 by x minus 4, but of course that's going to be the 3. So really I'm just going to multiply 3 by negative 4, and I will get negative 12. And then I subtract. When I subtract, what do we get? Negative 1. And then there's this little ghost, and I bring down the negative 6. And then, how many times does x minus 4 go into negative x minus 6? Well, it's going to be negative 1 time. So now you guys are kind of catching on that just like over here, the result of the subtraction automatically becomes the next coefficient in my quotient. Here, the result of the subtraction automatically becomes the next coefficient in my quotient. And then for the last time, I multiply through negative 1 times x, but I don't bother writing that because I know those numbers have to match. Negative 1 times negative 4 is 4. And then, this was controversial for some reason, but negative 6 minus 4 is negative 10. And so I got the exact same thing. Okay, take a minute to appreciate ghost polynomial long division. Do you appreciate it? Okay, all it is, it's the exact same thing, just with less writing. All right, is it actually any better? Like, probably not, because it's kind of like annoying, and so it actually takes me longer because it's like weird. But in principle, you could practice this, and you would get faster at it, because it does involve strictly less writing, yeah? Okay, well, now that I've mastered ghost polynomial long division, I look at this again, and I think, this algorithm still could be improved. Because there's all this empty space, taking up a lot of space on my paper. Don't you just feel psychologically like this all could be kind of just condensed or something like that? I feel that. And also, there's still some like unnecessary repetitions happening. Like I'm writing negative 13, I'm writing it again, I'm writing negative 6, and I'm writing it again. That's kind of like annoying. Okay, I hereby introduce you to an even more efficient algorithm. And this even more efficient algorithm takes advantage of what I've already learned here, which is that seemingly only the coefficients of the dividend matter, yeah? Okay, so keeping that in mind, I shall only write the coefficients. 6, negative 21, negative 13, and negative 6. Okay, and then I'm going to write this little thingy here. And then I'm dividing through by x minus 4. But instead of writing x minus 4, I'm just going to put a 4 over here in a little box. Okay. Yeah, it is. Okay, and so now watch this. Here's what I do. What was the first step in ghost polynomial long division? The very first step was the first coefficient of the dividend automatically becomes the first coefficient of the quotient, yeah? Okay, so the very first thing I'm going to do is take this 6 and just write it right here. Okay, so the coefficients of the quotient are just going to appear down here on this bottom row. All right, and then what was the next thing? So here's the first interesting part. What was the next thing I did with this 6? Well, I multiplied this 6, everybody with me, by negative 4, and then subtracted that result from negative 21. Instead of multiplying 6 by negative 4 and subtracting it from negative 21, why don't I just multiply 6 by 4 and add it to negative 21? That is the exact same thing. 6 times 4 is 24, and now I just add. And what do I get? 3. Okay, what do I do next? Notice that 3 becomes the next coefficient of my quotient, right? And here I just like save time by just putting it boom in the spot that I need it to be. Follow? Oh, okay, what else? Then, what am I supposed to do with that 3? I'm supposed to multiply that 3 back through, and I get 3 times negative 4 is negative 12. Well, instead of multiplying by 3 by negative 4 and getting negative 12, but then subtracting negative 12 from negative 13, let me just multiply 3 by positive 4 and add it to negative 13. That's the same operation. What do we get? Negative 1. Boom. I'm getting the exact same thing. Okay, and then what am I supposed to do with that negative 1? Send it back up to be the next coefficient in my quotient. And then I multiply that negative 1 by negative 4, which gives me 4. And then I subtract that from negative 6. Well, instead of multiplying negative 1 by negative 4 and subtracting it from negative 6, I'm going to multiply negative 1 by positive 4 and add it to negative 6, which gives me negative 10. Make sure I'm in frame over here. Probably am. Yeah. Good. All right. So what I need you to convince yourself of by a careful analysis, maybe you're already convinced, is that this process is just an extremely efficient and condensed version of ghost polynomial long division. Do you agree? Which is itself just polynomial long division. Okay, this thing has a name. This is called synthetic division. And if you're learning this for the first time right now, you're learning it correctly. We do not teach this in Pre-Calc A and Pre-Calc B, but some people do teach it. Perhaps you learned it in math team or middle school or outside of class or something like that. If so, I bet you did not understand why it works, because basically nobody does, but now you get it. The answer is sort of the logic of this algorithm is very hard to like extract, but I think that's what I've been trying to do here. Okay, good. What is the big point of why? So probably right now you're probably thinking, Mr. Rose, why should I care so much about synthetic division? It doesn't actually give me any new skill that I didn't have before. It's just the same thing as polynomial long division. Yes, however, the nice thing about it is it takes like a mere seconds. And because it takes a mere seconds, it's reasonable to do like a whole bunch of them. Like, I don't know, like 4 or 5 like per minute or something like that is not unreasonable. All right, and so the name of the game, what we're really trying to do today, I didn't tell you this yet, but I'm telling you right now, is find roots of polynomials. Okay, so this is what we want to do. Find the roots of the polynomial. Here it is. F of x equals negative 3x cubed plus 20x squared minus 36x plus 16. That's the goal. Okay? And for a moment, I would like you to appreciate how hard this problem is. Because this is a cubic. We have a quadratic formula, but we do not have a cubic formula. So we have no simple way of doing this. Also, there are no obvious symmetries. Do you see any factor by grouping opportunities here? I do not. There's no difference of cubes, there's nothing. So this is, I consider this to be a very hard problem. And we're going to spend the rest of the unit learning some techniques to figure out things about finding roots of polynomials. But before we do any of that, we are going to be guided by like a mystical bit of wisdom. And this mystical bit of wisdom is called the law of ones. And the law of ones says, oftentimes 1 is a root. Because nice people make fake problems, and they want the answer to be 1 because 1 is a nice small number. Okay, so we shall begin our quest to find the roots of this by checking to see if 1 is a root. And we're going to check to see if 1 is a root by dividing through by x minus 1. But instead of doing it the traditional way, we're going to do it in the synthetic division way. So here we go. Take the coefficients of this polynomial that we care about, write them out because only the coefficients matter, and then perform the synthetic division algorithm with 1. Okay, what is the algorithm? The very first thing you do is you just bring down the negative 3, multiply by 1, and you get negative 3. You write it over here, then say add. No, you don't try to add. Add, and you get 17.
Yeah.
Then multiply.
17.
Add. Multiply.
Negative 19.
Add. Negative 3. Uh-oh, what happened? There's a remainder, exactly. Okay, and specifically, what really happened, well, if you completely 100% trust the last 20 minutes of this class, then you know that synthetic division is just polynomial long division, yeah? Yeah. And so, what really happened over here in a very, very condensed form, what we really did was we took negative 3x cubed plus 20x squared minus 36x plus 16. We took that cubic, and we divided it by x minus 1, exactly. Justin says, remember, when we put a 1 here, that really means we're dividing through by x minus 1. Everybody with me? Okay, and what did we get out of this? Well, these numbers on the bottom are, in fact, the coefficients of the quotient. Cool? Okay, and so the answer to this problem is negative 3x squared plus 17x minus 19 minus 3 over x minus 1. Someone just whispered that's exactly correct. Whew. Okay, does everyone feel it? Synthetic division is just polynomial long division. So when you do that, you're really just doing this. Okay, well, translating this into a more helpful format, what we have really just learned is something about our function. What we've really just learned is that this function, negative 3x cubed plus 20x squared minus 36x plus 16, itself can be written as negative 3x squared plus 17x minus 19, the quotient, times x minus 1 minus 3. Who's with me? Please say yes. Okay, good. And therefore, what have I learned about what happens when I plug 1 into this function? What do I get back? Negative 3. Yeah. This is something that's known as the remainder theorem. The remainder theorem says if you have a polynomial and you divide that polynomial by x minus 1, which is what we did, and you get a certain remainder, negative 3. Negative 3 just is the value of that polynomial when you plug in 1. Okay, let's keep going. We got to finish. What does the law of ones tell us? When the law of ones doesn't work, we seek refuge with negative 1. So let's try that. Hopefully, surely this person wouldn't be this cruel. So okay, what do we do? I want to prove to you that these take about 5 seconds. We bring down the negative 3. Negative 1 times negative 3 is 3. Add. Multiply. So that's negative 23. Add. Negative 59. Multiply. 59. Add 75. Oh man, what did we just learn?
Negative 1 is
Negative 1
not a good either.
Yeah, this negative 1 is also not a root. What can we do? 2. Good choice. 2. Negative 3. 20. Negative 36. 16. Okay. Let's go. And what do I mean by let's go? We just do the algorithm. Algorithm says bring down the negative 3. 2 times negative 3 is negative 6. Add 14. Multiply 28. Add negative 8. Multiply negative 16. Add 0. Ding, ding, ding. Okay, what just happened? I'll tell you what just happened. We, once again, we took negative 3x cubed plus 20x squared minus 36x plus 16, and we divided it. This time we divided it by x minus 2. But this time, when we divided it by x minus 2, what came out? Negative 3x squared plus 14x minus 8. Like evenly, yeah? Say yeah. Okay, and so, once again, if you multiply both sides of this equation by x minus 2, what we really just learned is that this cubic function can be expressed as negative 3x squared plus 14x minus 8 times x minus 2. In other words, x minus 2 is a factor. And since x minus 2 is a factor, since it goes in evenly, then what is f of 2? 0. This is known as the factor theorem. The factor theorem says that if a number is a root of a polynomial, like if a number like 2 is a root of a polynomial, then x minus 2 must be a factor of that polynomial. Who's with me? Okay, and so what this means is that synthetic division doesn't just tell me, it tells me whether I have a root or not. It's just doing the polynomial along division in this special case. Okay, I have like 1 minute more worth of stuff to say, but maybe I should give up. I don't know, what do you think? Just give up?
2 minutes.
I have 2 minutes? Oh, that changes everything. All right. Good. Good. So wait, it's just, this is what I'm about to say is just kind of like a repeat of what I already said, but just more generally. So if you take a function and you divide it through by x minus k, and you get some kind of quotient, and you get some kind of remainder, we all agreed that the remainder is guaranteed to be a degree less than the divisor, right? But the divisor here is degree 1. So since the divisor is degree 1, what does that tell me about the remainder? Degree 0, in other words, it's a number. And so if you then multiply that through by x minus k, then this is kind of a more clear proof of the remainder theorem. F of k is r. The remainder after, just leave this here for a minute, the remainder after dividing a polynomial by x minus k is the value of f at k. And I'll just keep talking because no one can stop me. If you divide this polynomial by x minus k and it goes in evenly with no remainder, then that means that f is x times x minus k, and that means that f of k is 0. This is the remainder theorem, and this is the factor theorem. Alright. Everybody good? Yes, you can. Alright, anyone want to say goodbye to period 7?
Goodbye, period 7.
Okay, goodbye.
You got this. Life is wonderful.